Okay, folks, so this is lecture 15 of ECE3311, Principles of Communication Systems. So this is kind of deja vu all over again in terms of what we're covering. So we're covering amplitude modulation again. Yeah, but we're going to go into a little bit more details about how amplitude modulation works, okay? So there's some terminology that's associated with it, very specific to amplitude modulation. It's something that we use a lot in specifically AM radio, right? That all of you might have heard, especially if you're younger, if you're driving a car or if you're at home and you use one of those old school type of radios that you pick up wireless signals over the air. Okay. So in this lecture, again, we're going to go over some of the specific terminology of what amplitude modulation is. And then we're going to wrap things up, maybe do a problem or two, and then call it a day. All right. So let's get started. Okay. So again, amplitude modulation. So if we go back to the base waveform, and I changed what the passband signal representation is. Instead of V of t, it's S of t, all the same. Okay. So if we go if you use V of t or S of t, okay, we got this real operator, and we saw AC 1 plus m of t, okay, e to the j 2 pi fc of t, right? This is your message, okay? And your message, okay, if you, let's say, for instance, in AM radio, okay, in this case is human speech, it's voice, right? And human speech, for the most part, we can actually communicate from 0 to 8 kilohertz, right? If you could actually truncate that in half and communicate 0 to 4 kilohertz, but what will end up happening is your voice is going to sound very much like this and empty. 8 kilohertz, you capture some of the higher frequencies. It sounds like the voice has more presence, right? But 4 kilohertz is passable. That's what you see in sort of the old school landline type phones, right? It's a very bandwidth conserving, right? So if we have that message, right, the AM process, so here, that's your G of M of T. That's the mapping, okay, of that human speech signal to some sort of baseband representation that then gets modulated, okay, to a carrier FC. Okay, so this is really neat. Awesome. So we saw what happens is, so first of all, human speech, the M of T representation is a real value. So M of T, this is real, okay? AC, this is real. Obviously, the number 1 is real. So therefore, the mapping, okay, it's going to produce values that are real, okay? So let's keep that in mind. Because if we say, okay, if we want G of M of T, that mapping, so, and we go into the in-phase and quadrature representation, right? The Y value, okay, it's not going to have a complex term, right? So what ends up happening is we're only going to get this fella here, okay? And that's going to be equal to, okay, cool beans. So now, what do we know about that representation? So V of T now is equal to, okay, if we have that, we saw this before. This by Euler, okay, decomposes the cosine plus j sine. Okay, awesome. So this decomposes into what? This decomposes into x of t cosine 2 pi fc of t, okay, plus jx of t sine, okay. Then what we've got is plus jy of t cosine 2 pi fc of t, and then minus y sine 2 pi fc of t. So all I'm doing is I'm working it out. The real operator throws away the imaginary components inside the brackets, and all we're left with okay, this of course is 0, so that goes away. So this is what we get at the end of the day. Okay. Cool. That's totally awesome. 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 So that's my M signal, right? So what it does is, let's say, this is really recapping from the first time we were exposed to AM radio, right? Many, many moons ago, or lectures. It's not really moons. So if my human speech, frighteningly, looks like this, okay? So that's Wyglinski's speech. Okay, and that's from 0 to 8 kilohertz. Okay, what my AM radio is going to do is going to do a couple of things. So first of all, I create a bias. So I'm going to use a different color. What I'm going to do is I'm going to take all of this. Right now, the bias is at 0. I'm going to increase it by 1. Right? So move to 1. 1 from 0. And then the other thing is, if my dynamic range is this, with the A term, the AC term, I can either expand it or compress it, right? So if if this guy, okay, is greater than 1, I'm expanding the dynamic range of M of t. If it's less than 1, I'm compressing it, the dynamic range. So you might ask, why the heck I would want to compress or expand a dynamic range? This is why, folks. Let's jump into it. So let's say let's say I have a very loud voice. Oh, not very difficult to imagine. So let's do this. So let's say this again. Wig speech. Right? It's actually more complicated than that, right? So, and we take the dynamic range. So suppose the dynamic range in this case, right? Let's say that's 2. So let's say it goes, this goes all the way to like a value of -2. So it goes, amplitude decreases by 2. Let's say it goes up by 1.5 because it goes up to 1.5. So we have V max here, and we have V min there. And then we do this business, okay, of add 1. That's the first step of going from M of t to G of t, right? Add 1. Mu. So let's say the 1 mark. So all I'm doing is I'm increasing the bias. So let's say the 1 mark is here. That's 1. So what will this look like? And now my complete regret is that I should have drawn a much simpler version of my human speech. Anywho, it's going to look like this. Regrets. You know what? See? Now I'm using my brain. How should this look like? How about this? Yeah, that's it. Boop. 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 Yeah. Yeah. So now I increase the bias by 1. What I should get is something that looks like this. Yeah. Yeah, okay. All right. So this above the x-axis is positive. So plus VE is my shorthand for positive. Below is negative, right? Minus sign VE is negative. Okay, great, but not great, right? So if we don't do anything, we don't do that AC business. Let's say we set AC to 1. AC equals to 1, so we do nothing, AKA do nothing with dynamic range. Bad news. Because what that means is the following. Because now what we do is we're multiplying by cosine. So if we multiply by cosine, what are we doing? And I'm going to try and recreate. Yeah, see. Up, down, up, down, up, down, up, down, down. Okay, so yeah, something like that, right? People get what I'm, yep, there we go. So now if this here, that red is the envelope, and this is the cosine function I am modulating against. Here's its cousin. Ha ha ha. Now you're wondering, what is Wyglinski doing over there? Give me a sec. Okay. Envelope. This is the negative version of it. So what happens is, remember, cosine, right, is multiplying, and it alternates between 1 and minus 1, 1 and minus 1, 1 and minus 1. So it's multiplying against that envelope to create the amplitude value of it. So 1 times a value, it's going to be that value. Minus 1 times that value is going to be minus that value. Correct? So what ends up happening is we get something that looks like this. Okay? So we get this cosine, multiplies against it. Oh, look, this is so cool. So what happens is this really rapidly varying cosine creates a shape that looks like the envelope, right? Oh, hold the phone. When I hit the negative value, what happens? What's minus times minus? Plus, and then plus times minus, it's going to be minus. What happens is this segment here and this segment here, when it goes negative, it causes 180 degrees phase shift. This is bad news. So what was here? Oh, 180 degrees phase shift. Oh, now we go back. Oh, phase shift. Oh, phase shift. Cool, but not cool. Because now here's the problem. My receiver doesn't do very well in terms of handling phase shifts, right? This is actually the problem with something like this. So what ends up happening is, if I then do the receiver, like what we talked about, the envelope detector, what we're going to get, so what we want, okay, is something that looks like this. Let me try again. Take two. Something, right? Like that. That's what we want. That was the original. That was the original bias. So that's 1 plus m of t. Okay. This is what we'll get on happy face. So I already know what we're going to get. We're going to get something that looks like this. Boop. Boop. We're going to get this. This is the problem. It cannot discriminate between like that 180 degrees phase shift, the negative values. So that's the problem with the AM radio, like with AM in general, is that we have to be very mindful that the envelope clears that x-axis completely. It's almost like pole vaulting or some sort of gymnastic move or a sport or something what the heck is it? So I took gymnastics in high school. And that was scary. Like the pommel horse and, the long box and all that jazz. So if you go on the springboard and you don't clear it with your feet, this is the equivalent here with AM radio or just AM in general, is that if you don't completely clear that x-axis, you fall onto the mat on the other side. You can't recover that signal. So that's a problem. So that's where AC comes in. So how do I fix it in this case? What happens is, suppose I take the AC value, and what I do is I compress the amplitude of my waveform, right? So I make it smaller such that it's almost like I shrink the gymnast, right? So shorter legs, so that it can clear that pommel horse or whatever the shucks. What is it? I forgot what the name of the or a pole vaulting and stuff. So so what happens is those legs don't get caught on that piece of gymnastics equipment. That's what we're trying to do here. So if I compress that waveform, what ends up happening is I get some clearance because it's now not as drastic a dynamic range. So what I do is I shrink to clear x-axis. So that's what I do. All right. So that's sort of the goal of doing all of this is really to avoid that pesky x-axis business. So that way I don't have any no 180 degrees phase ambiguity. Okay. All right. So that actually segues very nicely into the rest of this lecture, right? Very importantly so, right? So the other things are, of course, the spectrum of what an AM signal looks like. This was actually the topic of class test 3. Some folks got it, some folks didn't, right? As well as the spectrum here. So what ends up happening is the spectrum, right? What does the spectrum look like? So what the AM radio spectrum is going to look like is something like this, or you're going to have your AM radio power spectral density, you have your AM radio, and then it's going to have the center frequency minus FC. So, and then we talked about, for instance, in that class test, like we had several radio stations, like 890 AM The Bear, and then you have like 920 AM The Moose, or 570 AM some other animal or something like that. What these refer to is actually the carrier frequency of the radio station, right? In kilohertz. So you might say, okay, where the heck are all these AM radio stations located? Well, let me bring it up. And of course, FCC, you're probably not seeing what I'm sharing, regulation chart, but that's fine. I'll get it in a second, folks. PDF. Let's find a PDF, because that's higher resolution. This is interesting. Actually, my apologies. I just really, if I can't find it, I will share it. This is kind of like spur of the moment. With regrets. And you're like, yeah, here we go. Okay, so let's download that as well. Okay, so bear with me, folks. You're probably like wondering, what is Wyglinski doing? Ah, perfect. Okay, there. You're probably seeing that. Let's get the other one. And awesome sauce. So all of you should be able to see the spectrum allocation charts here, or I hope. Okay. So let's see. So right now, what you're observing, this here. Well, let's see. Just double check. No, you're not seeing anything. There we go. All righty. So this here, okay, is the frequency allocation chart for the United States, right? So the federal government's responsible for the allocation and licensing of who accesses what frequency bands, because there are a lot of and a growing number of wireless applications out there, right? It started with like, the old school applications like AM and FM radio and radar and everything like that. But it's now proliferated to things like Wi-Fi and 5G and GPS and SATCOM and all these other types of wireless applications. So where's AM radio on this chart? Okay, well, here it is. I'm gonna zoom in. So yeah, see, so there's actually writing on it. It's like microscript font, right? So it goes by order of magnitude, 300K, then 3 meg, which is 3000K. Then 30 meg, or 30,000 kilohertz, and so on and so forth. Okay, so you get my drift in terms of like. So now let's zero in on AM radio. So that big humongous blue thing, if you like zoom out, like, and it's just like near the top, that, folks, is AM radio, right? It goes from 535 kilohertz, all the way to 1606, but actually continues. So it shares a sliver with mobile applications, and actually chugs all the way along to 1705 kilohertz. So that's AM radio in the United States. So those bands are licensed to AM radio applications, and you have, if you're a legit AM radio station, you got to get that license from the FCC. But if you aren't legitimate AM radio station, you got to play nicely in that band and follow all the regulations that an AM radio station should, including power level and not interfering with other AM radio stations. All right. So that's the spectrum allocation for AM radio. And okay, so here's the thing. this is deceptive, right? So you have this like humongous swath of spectrum. But again, remember, we're going by order of magnitudes, right? So like as we progressively go up and up and up, it looks big, but it's actually not. So, 300K to 3 megahertz. Yeah, that's kind of big, right? But then we go from 3 megahertz to 30 megahertz, right? So these things are progressively getting bigger and bigger as an order of magnitude. You can also go crazy, like what I just did before with the FCC table. So I'm going to be putting these up on the course Canvas website for everybody to enjoy. But this, okay, is the document that also guides that table, right? So you can find out exactly, if in case you want to do it in writing rather than in than visually, exactly where everything's located across different frequency stretches in the United States. Right? And you might say, up to how far does the FCC govern this? Well, FCC is all spectrum, but in terms of like for wireless applications, usable spectrum's up to like 300 gigahertz. After that, we start going into like visible light, and that's like super duper, like highly directional. So I don't want to say, oh, well, you don't have to regulate that. You do, but for like omnidirectional electromagnetic energy and stuff that a lot of commercial applications use, this, folks, okay? Anyways, I digress. I just wanted to bring that up, right? Because like, where did those AM radio stations come from? Alrighty, going back. So that's what the spectrum looks like. We saw this, the AM representation, so it should not be a surprise to anybody. So this again goes to the percentage of positive modulation, percentage of negative. So what this represents, right, the A max and the A min is that dynamic range I was telling you about, right? Like what should A be, and how do we deal with like how much of it goes above and how much of it goes below, right? The like over the whatchamacallit, over the x-axis, right? And so we talk about like, percentage of how much of it goes up, exceeds, and how much of it goes below that x-axis. So we call it the percentage of positive and negative modulation. And again, that's an issue if you want to avoid any phase ambiguity. We also calculate what the average power is of an amplitude modulation signal, right? And its modulation efficiency. Okay. So these weird brackets represents the average. Okay. So what does that mean? Well, what happens is the way average is calculated. Okay. So there's both, there is a statistical average, and that's kind of a bad choice here using E for that. But those brackets, if I do this, okay, that's the average value of M of t over t. So if I have something that looks like this, okay, what's the average? So what I do is over this time period, if whatever is active, right, from T1 to T2, what I do is I calculate what the average value is across all those points of that signal. So that's what the angled brackets M of t represents, right? So of course, and so what the modulation efficiency is, okay. And it's squared. Sorry. Okay. So mu 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 mu. There we go. Sorry. What the modulation efficiency is, you take the square of this waveform. So what that does is it gets rid of the negatives. And then it's plus. Okay, yeah, that makes sense. Okay. And then 1 plus that. and then times 100%. So it's a ratio. And so this will give you the modulation efficiency, represented by E. The reason why, as an aside, I was kind of like, bad choice for E, is because E, okay, is also used as an average, but this is when X, okay, is what they call a random variable. Okay, so it too, E, the expectation, if you ever take probability, expectation, AKA the average. So that's why I'm a little bit, I was like hesitant saying, Okay. Now let's switch gears back. Okay. And then there's peak envelope power. So the maximum value, so that's the highest value. Okay. And then we take 1 plus that. So what this tells me, the peak envelope power. So what's the relationship between voltage and power? It's a square relationship. So you find the largest possible value for M of t, right? You take the square of that. Sorry, you find that value. You then modulate it to the envelope, and then you square it, and that gives you the square of that. That gives you the peak envelope power. All right. So a lot of definitions. All right. So that concludes AM modulation. So what we talked about here in this lecture, right, is this idea of doing this this thing called amplitude modulation. It's relatively easy in terms of like, how do we get about it? In this case, there's a DC bias. Then we multiply it by AC. And then we multiply against a cosine. So cosine can be generated very easily, right, off of like a local oscillator. And that's what we send over the air. And then likewise, what we saw earlier, okay, in I forgot which lecture it was, in terms of detectors, recovering that message signal M of t is also relatively easy. We pass it through a square law device. We then take the output of that square law device. We low pass filter it to extract out just the baseband component, which will be G of M of t. And then we take the square root of that, okay, to get G M of t. Otherwise, we get G M of t squared. And then we divide it by AC, and then we subtract off the bias to get M of t back. All right. So that concludes lecture 15 of ECE 3311.